In this video, we're going to talk about momentum. Now, momentum was originally thought of by, I believe, Galileo as the quantity of motion. How much motion does something have? And he thought it depended on two things: how much mass it has and how fast it was going, or its velocity. So momentum is defined as a vector quantity and it's a product of the mass times the velocity. It is a vector. Momentum has a direction. That simply makes sense to us. If something, if a football player is running downfield, the direction of his momentum is obviously the same as the direction that he's running. It is a vector. It has SI unit. In this case, there's not a special unit. It is simply a product of mass, which is kilograms, and velocity, which is meters per second. So it's a kilogram meter per second. There's not a quick, easy shorthand. One interesting aspect is that Newton's second law, that's that F net equal ma, was originally defined in terms of momentum. He wrote it like this. The net force is the derivative of the momentum with respect to time. If we think in terms of an average momentum and a time interval, this looks like this. It is the change in momentum with respect to time. So that's how he defined it. However, we think about what does it mean to have a change in momentum. It's possible in situations for the mass to actually change and to have a situation where both mass and velocity are changing. A perfect example would be a rocket that's actually burning fuel so that its mass is a function of time as well as its velocity. But if we take that possibility off the table and we assume we're talking about something that has a fixed mass, we get this situation. And we know that the change in velocity over the change in the time then is just mass times acceleration. The honest part is you don't need to know any of that, but I just think it's interesting. What you do need to know is that momentum is mass times velocity. Another thing that we've probably used this word a fair amount already, but the idea of a system. A system is a collection of objects. The momentum of a system is simply the momentum of each object in the system. So if you want the total momentum of a system, it is simply the momentum of the first object plus the momentum of the second object plus the momentum of the third object. And of course, these are vectors. So it's not simply adding them up per se, it's a vector sum where you have to really think about direction. Now, we're going to keep our system small. How small? 2 objects. It gets really complicated if we let more than 2 objects in our system. So let's just find the total momentum of a system that has 2 objects. This is straight out of your textbook. It says we have a 1,000 kilogram car traveling north. I'll put moving, that's a little shorter. At 15 meters per second. We also have 2,000 kilogram truck moving east at 10 meters per second. For now, it goes on to say that they're going to have a collision, but for right now, all I want to know is how much momentum does my system have? Sometimes it helps to draw a picture. So we have the car moving north. And of course, its mass was 1,000 kilograms. And its speed was 15 meters per second. And we have this truck, a little bigger. It has a mass of 2,000 kilograms. And of course, it has a speed of 10 meters per second. We have two vectors that don't point in the same direction, but it's pretty easy because they are perpendicular to one another. So if we want to think about the momentum that's horizontal, just the x component, mass times velocity, and we get 20,000 kilogram meters per second. If we want to think about the y direction or vertically, north-south, we have a mass of 1,000 kilograms going 15 meters per second, and that's going to be 15,000 kilogram meters per second. Since we have perpendicular vectors now, we have the x and y component, we just use the Pythagorean theorem. We know the magnitude of the momentum is what we get when we do 20,000 squared plus 15,000 squared. Interestingly enough, comes out pretty easy. That is going to be 25,000 kilogram meters per second. I don't know if you recognized it, but this actually makes the Pythagorean triple. 15,000, 20,000, and 25,000. That's a 3, 4, 5 triangle that's been multiplied by a factor of 5,000. The angle, it's the tangent inverse, y over x. The y was the smaller number, so 15,000 over 20,000. And we get an angle here of 36.9 degrees. We could have just written 37 if we like. So that was simply just a vector sum. Okay, it was nice because the two vectors we had to add, the car and the truck, they were already perpendicular to one another. Okay, carry on. Conservation of momentum. There are 4 basic conservation laws in physics. We've already talked about conservation of energy. We also have conservation of momentum, conservation of mass, and I've drawn a blank on what the 4th one is. I'll come back to that, but let's go on for right now. Right now we're just interested in talking about conservation of momentum. All right, what that law basically says is the momentum of a closed, isolated system is constant. Okay, the momentum of a closed, isolated system is constant. A closed system simply means we're not going to let any new objects leave our system or enter our system. So if we're going to have a system with two objects, we're not going to add anything to that, or you're changing the system. I know sometimes there's problems where a snowball rolls downhill and gains mass. Well, if the snowball's gaining mass, you're adding new matter, new particles to your system. So we couldn't do that. We're going to just have two objects, nothing else comes. Isolated. An isolated system has no external forces. That's what that's saying. That's a really important idea. There can be no external forces. It's really important then that we understand the difference between an internal force and an external force. Internal forces are between objects in the system. An external force is exerted by an object outside the system. Here's a really simple example. This purple marker in my hand, if this purple marker is the only item in the system and I drop it, notice that right now it has no momentum, but if I drop it, it gains speed on the way down. Its momentum is increasing. Why is its momentum increasing? Well, it has an external force. That external force would be gravity. Okay? The marker is gaining downward momentum. Now, if I change the system and say, oh, I didn't mean for the marker to be the system, I want the marker and the earth, those two objects, just the marker, to be the system, well, then that force is an internal force. And we see that the total momentum of the system is still constant. The marker gained a downward momentum, but the earth would gain an upward momentum because it feels an equal but opposite force up. Momentum would still be conserved. So it's really important when you look at problems that involve conservation, like conservation of momentum, that you have a well-defined system. Okay? If you have two objects and they interact with each other, if they're part of the system, that does not change the momentum. Internal forces will not alter the momentum, even if the internal forces are not conservative. So even if the kinetic energy or the mechanical energy of the system changes, momentum is still conserved. That's really important. It means momentum is conserved in situations where mechanical energy might be lost to heat, to non-conservative forces. Okay? Internal forces do not change the momentum. However, external forces will change the momentum. Look at An example. This is an example of a type of problem where the initial momentum is zero. I often call these explosion problems. Even though there doesn't actually have to be what you and I think of an explosion, we generally have a situation where, we'll pretend like this is a gun and a bullet, where the system has no momentum. Let me see, both the gun and the bullet are at rest. But if there's an explosion and we fire the bullet will gain momentum in one direction, and the gun will have a recoil velocity, a recoil momentum in the opposite. In other words, when I think of an explosion, I think of something that's at rest, or a system at rest, and then things go moving apart in opposite directions. So in this case, we have a situation of an astronaut who is 100 meters away from her ship when she becomes untethered. I think we've seen that in the movies. So, we have an astronaut. She's 100 meters from the ship. She becomes untethered. She has 20 minutes of air. So she needs to get back to her ship in under 20 minutes or she's gonna die. She happens to be having, well, let's just go ahead now. The mass of the astronaut, with all of her gear, everything she's wearing, is 100 kilograms. She also has a wrench. And the wrench has a mass of 10 kilograms. So that's a pretty heavy wrench. So her mass plus the wrench is a total of 110. So not including the wrench, she's 100 kilograms. Oops, sorry. 1 kilogram wrench. That makes more sense. That's still a heavy 2-pound wrench. So astronaut's 100 kilograms, wrench is 1 kilogram. What's she gonna do? Well, here's a picture. Here's her little space shuttle thing. She wants to get back to it. Here she is, floating around. What she's going to do is she's going to take this wrench and she's going to hurl the wrench as hard as she can away from the ship. So she's going to send the wrench this way, to the right. Here goes the wrench. It goes flying. She's going to throw it at 10 meters per second. Let's see if we can figure out whether or not she's going to make it back. If we use conservation of momentum, the initial momentum has to equal the final momentum for your system. Well, the initial momentum of this system was 0. The astronaut was at rest, the wrench was at rest. The final momentum, the way I drew the picture, the wrench is moving to the right, so the mass of the wrench is 1 kilogram. The velocity of the wrench is 10 meters per second, plus the mass of the astronaut is 100, and the velocity of the astronaut is what we want to find. If I move this over, I'm going to get negative 10 equals 100, velocity of the astronaut. So she's going to move to the left or in the opposite direction at negative 0.10 meters per second. She's not going very fast, but she's going. The real question then is, if she's going at 0.10 meters per second, can she make it to the ship in time? We know she only has 20 minutes of air, If I do that times 60, 20 times 60, she has 1,200 seconds to get back to the spaceship. Her displacement, if you've got a constant velocity times time, she's traveling at a speed of 0.10. She has 1,200 seconds. Okay, let's not even do that one. Let's do it this way. Let's do it. We know she wants to travel 100 meters. And we know that she's traveling at a speed of 0.1 meters per second. The question is, how much time will that be? Well, our time is going to be 1,000 seconds. Well, we already said this was enough air for 1,200 seconds. So yeah, she's good. She's got 200 seconds to spare. That's like over 3 minutes. She's in good shape. It's going to take her like 16 minutes and 40 seconds. Let's do one more. This is the other type of problem. The other type of problem is a collision. So, when you have an explosion, we start with no momentum, and we end with a total of 0 momentum. If one thing gains 100 kilogram meters per second, the other thing loses 100 kilogram meters per second. In a collision, we start with momentum and very likely, although not necessarily, will end with momentum. In this case, we've got two gliders on a frictionless track. Here's glider A. It's moving this way. Here's glider B. It's moving the opposite way. The mass of A is 0.50 kilograms. B is 0.30 kilograms. They tell us that glider A starts off with an initial velocity of 2.0 meters per second. Glider B has an initial velocity of 2.0 meters per second to the left. Okay, folks, that's really important. What that means is negative 2.0 meters per second. We have to pay attention to signs when we're working with momentum because momentum is a vector quantity. Okay. They also go on to tell me that after they collide and they bounce off of each other, that glider B is moving 2.0 meters per second to the right. So now, after the collision, B bounces back, it's got a positive. They want us to find the answer to the question, what's the final velocity for A? We're going to use this whole idea, conservation, that the initial momentum must equal the final momentum. So let's go. The initial momentum, 0.50 times 2.0. That's the initial for glider A, plus 0.30 times negative 2.0. That's the initial momentum for glider B. Momentum of A plus momentum of B. After the fact, it has to equal momentum for A, 0.5, times this final velocity we don't know, plus for B, 0.30 times 2.0. So I know everything. Mass times velocity for A, initial. Mass times velocity for B, initial. That's my initial momentum. Mass times velocity for A, final. I don't know that number though. Mass times velocity for B, final. That's going to be 1 minus 0.6. This whole thing comes out to be 0.4. That's the momentum of the system had before we had any kind of collision. Obviously, that's the total momentum of the system. Afterwards, this is 0.5 VA final plus, that's 0.60, that's kilogram meters per second. All right, if we subtract the 0.60 from both sides, I'm going to get 0.20 equals 0.5. And when I solve that, oh, this is negative. It's going to be negative 0.40 meters per second. Notice if we think about this for a minute, it makes sense. It'll be going to the left. The total amount of momentum, let's think about how much momentum things had before and after. Before the collision, block A had 1 kilogram meter per second, mass times velocity. After the collision, it had negative 0.20, mass times velocity. So it went from positive 1 to negative 0.2. That's a change of 1.2. Go from positive 1 to negative 0.2. Let's see what glider B did. It started with 0.60, or negative 0.60, because it had 0.30, negative 0.20. It started with negative 0.60. Afterwards, it's still 0.30 times 2, but it's positive 0.60. If you go from negative 0.6 to positive 0.6, that's a gain of 1.2. So glider A lost 1.2 kilogram meters per second of momentum, but vector B gained 1.2 kilogram meters per second. All makes perfect sense if we're thinking conservation of momentum. Okay, I'm going to stop this video here. We'll continue the rest of chapter 8 in a second video.